Hello everyone, today let's just take a look at QP92, just proving some useful facts about expectation and variance. So first of all, in part A, we're proving linearity of expectation. So that's just the fact that the expected value of when you add two random variables is just going to be equal to the expected value of one plus the expected value of the next. So when we take the expected value of a constant times a random variable, we can just pull the constant out. So this one shouldn't be too complicated, but we have x and y here that are discrete random variables on the same probability space. So let's let this be a probability space or just a drawing of it. And the definition of a discrete random variable is just something that takes some outcome in our probability space and assigns it some value for every single possible outcome in the probability space, right? So all that means is that x and y both partition our sample space. So for instance, for x, maybe it partitions our sample space like this, and then it assigns this probability mass up here the value of 1, maybe this one over here the value 2, maybe this one the value 3, and maybe this the value 4. And these are obviously just arbitrary just for the sake of drawing it out. And then y is another discrete random variable in our probability space, so it must partition it, which means maybe it looks something like this. Maybe up top here we have y equal to 1 in this blue region, and then maybe on the bottom we have y equal to 0, something like that. So now because x and y fully partition our sample space, there's no overlap between the different x values and there's no overlap between the different y values. What that means obviously is that omega, the totality of our probability space, is just comprised of all of these different little subregions, the union of all of these green regions in here, right? So more formally, omega equals the union over all I and j, where I are the values that x can take and j are the values that y can take of x sub I intersection y sub j. So for the expected value of x plus y, let's just first look at an example up here in this green shaded region. When we're in this green shaded region, it's the intersection of when x equals 3 and y equals 1. So when I'm in this region, obviously x plus y is equal to 4, 3 plus 1, and the probability of this green event occurring would just be the probability of intersection between y equals 1 and x equals 3. So when I'm taking the expected value of x plus y, I just want to repeat that process for every single one of these sub boxes. So I'm just going to take the sum over all values that x can take I and all values that y can take j of the actual value that I'm trying to find, which is x plus y, and then weight that by the probability of intersection between x equals x sub I and y equals y sub j. And then obviously I can just distribute this right here inside of this term, so I'll get the sum over ij of x times this probability plus the sum over ij of y times this probability. Now next we can actually expand this double sum, so let's go down and do that here. This is the same formula, I've just expanded these as a double sum. We're still doing the same thing, we're summing up the weighted probabilities for each of these boxes here. So now if we look at this part right here, well, x right here is a constant relative to this iterator. It's only iterating through all the y values, so we could just pull x out of this internal sum. So this is what that would look like, and now we can just use the law of total probability on this part right here. This is just going to be equal to x times the probability that x is equal to x sub I. Again, this is just from law of total probability. We know that y partitions our entire sample space, so y must partition x as well. So for every x value, let's say x is equal to 4, we know that y partitions it. In this case, this part would be when y is equal to 1, and this down here would be when y is equal to 0. So if we just take these two intersections and sum them up, this one plus this one, we get the total probability that x is equal to 4. So this right here is what that green part equals here, and now we just need to take the sum over all x, and we know that the sum over all values of x times the probability that x is equal to that value is just called the expected value of x, right? And then it's going to be the same story for the other side of the equation. We know that we could just rearrange these sums because of properties of addition, obviously. And now if I look at just this part over here, I know that I can pull the y out because it's a constant relative to the iterator. And then again, for this term inside the sum, I'm just going to use the law of total probability. So in our example, if we have y equal to 1, so we're up here, well, we know that x fully partitions our sample space, so we just sum up all of these individual contributions of the intersections, and obviously we're just going to get back the total probability that y is equal to 1. So this part here is just equal to the probability that y is equal to y sub j. Again, one more time, just the law of total probability, and then we're going to multiply it by this y value. And then when we take the sum of this, we iterate over all the y values of y times the probability that y is equal to that value. Well, that's just the expected value of y. So that's how you get the fact that the expected value of x plus y is just equal to the expected value of x plus the expected value of y. So this property is really useful. And also notice that we never used any assumptions about the independence of these variables, right? They didn't have to be independent. So even if two variables are totally dependent and you're trying to find the expected value of their addition, you can still decompose it into the expected value of x plus the expected value of y, and that's also really useful. Now also this one's super easy, but let's just briefly do this. What's the expected value of a constant times x? So this is what it looks like if we just use the definition of expected value. Now since we're just multiplying every single outcome by some constant, the probability of that outcome is not going to change at all. So this is just going to be equal to the probability that x is equal to x sub I when we have I in x. Now clearly c is just a constant, it does not depend on our iterator. We can just pull that out and then we just get c times the expected value of x right here. So it's just equal to c times the expected value of x. Now instead, let's look at the case when we're trying to take the expected value of x times y. So this is what it would look like just by the definition of expected value. We weight each value that we're trying to find by its probability of occurring. Now, since we were doing addition before, we could distribute this and kind of break it up that way, but now in this case, there's no real way to simplify this. However, if we knew that x and y are independent, just by the definition of independence that we've already talked about, we know that this is just going to be equal to the probability that x is equal to x sub I times the probability that y is equal to y sub j. So if they're independent, then you can write out this equation like this, where I've just expanded out the double sum and just rearranged these terms. And then these terms right here only have x in them, so relative to the iterator for y, this is going to be a constant. So that just means I can pull this term out from here if I do it like so. And then also for the same reason, this entire term over here is going to be constant relative to this iterator. So that means we can just pull this entire term out of that summation out there, and we can just multiply these together. And what do you know? This is the expected value of x, and this is the expected value of y over here. So when x and y are independent, the expected value of x times y is just equal to the expected value of x times the expected value of y. All right, so now let's just do the variance identity, which will be part C. I ended up adding the part B about the multiplication for the expected value. So the variance is just measuring the average squared distance from the mean. It's squared because we don't want to deal with absolute value and we don't want to deal with negative numbers. So this one should be pretty simple. With the variance of x, we're taking the expected value, so the weighted average over all the possible values that x could take of this value inside here. I'm just calling the expected value of x the mean. I'm just going to call that mu, so it's easier to write out. Now we can just expand this term in here. We get x squared minus 2 mu x plus mu squared, and then we just multiply that by this again. Now we can just distribute this inside here, obviously. And this is what we get down here. This is obviously the expected value of x squared. For this middle term, 2 mu is a constant relative to our iterator again, so we can pull that out, and then we just get 2 mu, and then in here we have the expected value of x, so 2 mu times the expected value of x, but the expected value of x was just equal to mu, right? We were just writing that in. So this term right here is just going to be negative 2 mu squared. And then for this term over here, again, we can pull the mu squared out because it's a constant relative to our iterator. And let's do it like this. And we also know that x is a random variable that fully partitions our sample space. So when we sum up all the probabilities, that's just going to equal 1. So this term right here is just going to be equal to mu squared. So now I come down here and I simplify, I get that this is equal to the expected value of x squared minus 2 mu squared plus mu squared. So that's just going to be mu squared. And we were just using mu as a shorthand for the expected value of x. So this term right here is just going to be the expected value of x all squared. So that concludes that proof. So yeah, all three things in this problem are going to be very useful later on, so they're good to know now.